Hi everyone, welcome to the another session on low power VLSI design. In previous sessions, we discussed dynamic power dissipation and types of dynamic power dissipations. And now coming to this another type in power dissipation, that is the static power dissipation. So majorly the static power dissipation. The static power dissipation is also known as leakage power dissipation. So the definition for the static power definition dissipation is the power consumed by the CMOS circuit even when it is not in the switching state. That is, the device is in the on state only, but that is not doing any action. That is not in the switching state. That power is called static power dissipation. That is, the device is on, but there is no switching. Means there is no changing in the signals. So normally in CMOS circuits in steady state, there is no direct path from VDD to ground. So there should be no static power dissipation. But there are various leakage current mechanisms which is responsible for static power dissipation. So, due to this reason only static power dissipation is also called as leakage power dissipation. So, majorly it is focusing on leakage powers only. Means the device is in on, but that is not doing any switching. So, mass transistors are not perfect switches. There will be leakage currents and at substrate injection currents which will rise the static power dissipation in CMOS circuit. So if you observe here, the leakage currents are normally negligible in order to nanoamps compared to the dynamic power dissipation. But coming to this, whenever we are using this uh, technology, means technology is shrinking, that is deep submicron technologies, the leakage currents are increasing drastically to the extent that in 90 nanometer technology, and thereby leakage power is also has become comparable to the dynamic power dissipation. Generally, these leakage currents are negligible, but coming to this technology, whenever the technology is shrinking, uh, the leakage currents are also more, and those are nearly equal to the dynamic power dissipation. And the leakage currents, different types of leakage currents are subthreshold leakage and gate oxide leakage, junction leakage. Majorly, that is subthreshold leakage and junction leakage occurring at the junction and occurring at that gate, that is called gate oxide leakage. So here this is the diagram related to the static power, and by using this diagram we can observe the possible ways of different types of leakage currents. So here in this is the structure of mass device. So these are the terminal, source, gate and drain. If you observe, so these are the different currents I1, I2, I3, I4, I5, I6 and I7. So these are the different currents, and this is the gate terminal, and this is the polysilicon is acting here gate, and this is the SiO2 layer. So leakage currents in mass inverter having several leakage mechanisms. Those are responsible for the static power dissipation. So majorly here, first of all observe I1, I1 and I2. I1 is nothing but reverse bias I1, reverse bias PN junction diode leakage current. So if you observe, this is consider this is any PMOS or NMOS device. If you take uh, this is the NMOS device, and here the substrate is the P, and the source and drain are the N. So, because of this, these two are forming the PN junction diode. So, I1 is called as reverse bias PN junction leakage current. So, these two are forming the P and N regions. So, this is the reverse bias PN junction leakage current. I2 is also reverse bias junction current due to the tunneling of the electrons from valency band to the conduction band. That is from one region to the another region. Valency band present in the P region to the conduction band of the N region. So these two I1 and I2 are the occurring at the junction. This is forming the P and this is the N. Both are PN junction. So these two are I1 is forming the reverse bias of the diode leakage current. I2 is the tunneling of the electrons from P region to the N region. And coming to this I3, and this is the important one. This is called subthreshold leakage current, and this will be happening between the source I3. This is the happening between the source and the drain. So whenever the gate voltage is less than the threshold voltage. So here, we need to apply the voltage at the gate terminal. Whenever this voltage is less than the threshold voltage, generally threshold voltage means the minimum voltage required to operating the device. The minimum voltage required to conducting the device is called threshold voltage. Generally, if you consider the example, take that PN diode, the minimum voltage threshold voltage cutting voltage 0.7 volts. That is the voltage required to conducting that diode. So here also, if you are applying the voltage less than that minimum voltage, then the leakage is possible. That leakage is called subthreshold leakage. So this is called whenever your input voltage is less than the threshold voltage, that is called subthreshold leakage current. That is the I3. Next, I4. I4 is called oxide tunneling current due to the reduction in the oxide thickness. So here this is the SiO2 and this is the polysilicon. So if you reducing the thickness of this SiO2 layer, there is a possibility of tunneling the current from gate to the this region. Because of that one, it will leakage in the current. That is the oxide tunneling current leakage. And I5. I5 is nothing but gate current due to the hot carrier injection of the electrons. That is I gate. So whenever you are applying the voltage at the gate, now because of that more value, the carrier's electrons will injecting from one side to the another side. Means from this position to the they are moving towards the substrate. Because of this also, it will leakage the current. That is the I5. Next, I6. I6 is the gate induced drain leakage current. Gate induced drain leakage current due to the high electron field due to the affecting at the drain junction. So this is the drain junction. This is affecting from drain junction to this source side. So gate induced drain leakage current. And I7 is nothing but punch through. So punch through current due to the close proximity of drain and source. So close proximity, if the whenever the technology is shrinking, technology is nothing but it is indicating the distance between source and drain. Whenever these two are very near, source and drain are very close due to the close proximity of drain and source. In short channels, this will occur punch through leakage. So these are the different types of leakages, and these all comes under static power dissipation only. I1, I2, these two are occurring due to the reverse biasing of the PN junction diode. So here this will form, this is the P and this is the N. So reverse bias PN junction diode and tunneling of that electrons from P region to the valency band to the conduction band. And I3 is nothing but whenever your input voltage, gate voltage is less than the minimum voltage, threshold voltage, this subthreshold leakage current will occurs. And I4 and I5. I4 and I5 is nothing but oxide tunneling. Whenever you are decreasing the oxide thickness, then there is a possibility of electrons moving from gate side to the substrate side. And I5 is also whenever you are increasing the voltage at the gate terminal, then also the possibility of moving of the electron field from one side to the another substrate side, then it will releasing the some leakage current. And coming to the I6, drain induced gate or gate induced drain leakage. This is also occurring due to the drain junction. Drain junction, it will occurring between the gate and drain. And final last one is the channel punch through. This is the I7. This is depending upon the closeness of that source and drain. And majorly we are observing this I7 in short channel devices. So these are the different types of leakage currents present in the static power dissipation. So here these are the different types of leakage currents. So apart from these four primary leakages, there are fewer other leakage currents also that can contribute in the static power dissipation. Thank you. This is about static power dissipation.